once that we have seen the most basic Z transforms, let's talk a bit about the properties of the Z transform. So the first property that we consider is linearity. So I just used linearity when I computed the Z transform of the sinusoidal function. Linearity basically means that if you have the Z transform of a linear combination of two sequences, this is equal to the linear combination of the Z transforms, okay, of the two Z transforms. This is obviously a very useful property, as I just shown in the sinusoidal function, but this is also fundamental. If we didn't have this property, we wouldn't use the Z transform to study linear systems, because we will break the linearity property. The second property that we look is the multiplication by e power k. So this means that, let's say that we can compute the Z transform of the sequence x of k. So we know this Z transform, and this Z transform is capital of Z. Okay? Now, without doing again the computation, we can claim that the Z transform of x of k multiplied by a power k is just the same Z transform, so the one that we have just computed, just replacing Z with Z divided by a. The proof is quite straightforward and is here. So the Z transform of a power k x of k is by definition the sum with k that goes from 0 to infinity of a power k times x of k times z power minus k. Now, what we can do here is that we can put a power k and z power minus k together like this. Okay, so this is a factor power minus k. You see that this is z power minus k, and this is 1 over a powers minus k, that is actually equal to a power k. Now, at this point, we recognize that this is actually a Z transform. We just have to consider as a variable Z divided A instead of just the original variable Z. And so this is actually a Z transform where instead of the original variable Z, we have Z divided by A. The next property that we consider is the shifting theorem. So this property is fundamental, and this property is the equivalent has the same importance, okay, of the property of the Laplace transform of the derivative of the function in continuous time. So the Laplace transform of the derivative of a function in continuous time is a fundamental property to study the solution of differential equations. Here is exactly the same thing. The shifting theorem is fundamental to study the solution of difference equations, because it allows us to write the shift in time, so how it happens basically in difference equations of a sequence. The shifting theorem is stated here. So this is the shift towards the right. Okay. In this shift, we want to compute the Z transform of x of k minus n. And this is actually equal to z power minus n x of z. So first of all, what we are actually doing. So let's consider a sequence, and let's consider, for simplicity, the step function. So x of k, here it's 1, 1, 1, 1, and here it's 0, 0, 0. Now we shift this function. And this will be the function x of k minus 2. Okay? So how do we compute x of k minus 2? When k is 0, we have x of minus 2, and x of minus 2 is 0. So when k is 0, here we have 0. Then when k is 1, we have x of minus 1. X of minus 1 is this one, and is 0. When k is equal to 2, we have x of 0. So we are here, and we say that x of 0 is 1. When k is 3, we have x of 1 is 1, and so on. Okay? On the other side, when k is minus 1, this is x of minus 3, and so we have 0, 0, and so on. So we see that this shift is a shift towards the right. Now we want to compute the z transform of the shifted function without actually doing the whole computation by using this formula. So the proof is the following. So the z transform of x of k minus n is equal, by definition, to the sum of k with k that goes from 0 to infinity of x of k minus n z power minus k. Okay? Now what we do is the following. We multiply and divide by z power minus n. So let's write it on the board, because then there is another step that is maybe less clear on the slide. So we have that the z transform of x of k minus n is equal to the sum with k that goes from 0 to infinity of x of k minus n z power minus k. So this is the definition of the z transform of this. Now what we do is that we multiply and divide by z power n. So we have z power n divided z power n, and here we still have z power minus k. Okay? In this way, we can actually write this as we bring this z power minus n outside. We can do it because this z power n minus n, sorry, does not depend on k, so we can bring it outside the sum. So we have z power minus n, and then inside we have k minus 0, infinity, x of k minus n, and then here we have z power n times z power minus k, and this can be written as z power minus k minus n. Okay? Now what we do, we make a change of variable, and we define the variable m equal to k minus n. So in this case, we can replace this k minus n with m, and the same here, but we have to replace also this k here. Okay? So if m is equal to k minus n, then k is equal to m plus n. Okay? And when k is equal to 0, then m plus n is equal to 0. And this means that m is equal to minus n. So this means that this sum can be written as z power minus n. We don't touch what is outside the sum. And then we change the variable inside the sum. So we have that m goes from minus n to infinity. Here we have x of m, and here we have z power minus m. So here we almost have a z transform. The problem is that here m goes from minus n to infinity instead of 0. But let's consider the fact that for all, this symbol means for all m less than 0, x of m is equal to 0. Why? And the reason is that for all negative values of the discrete time, we have assumed that the function is 0. So in this way, we actually have that this expression is simply equal to z power minus n, the z transform of z. And we have proved the theorem. Okay? Then we want to prove the shifting theorem also when instead of shifting towards the right, we want to shift the function towards the left. Okay? This case is a bit more complicated. So in this case, we represent x of k plus 2. Okay? And so we see that when k is minus 2, we have x of 0. And so let's put the numbers. Minus 1, minus 2, minus 3, 1, 2, 3. So when this is minus 2, we have x of 0, and then we have 1. When this is minus 1, we have x of 1, and we have 1. When k is equal to 0, x of 2, and we have 1, and so on the right. On the left, when k is equal to minus 3, then we have x of minus 1, and so we have 0, 0, and so on. So we see that we have shift towards the left. Now, what is the problem? What makes this more complicated? The thing that makes it more complicated is that we are breaking our assumption that the signal is 0 for negative values of time. So when we compute the Z transform, we have to somehow fix this issue. Okay? So the expression, as you can see from the slide, is more convoluted. Okay, let's find it. So let's demonstrate this expression and then to explain how this issue can be taken into account. So we want to compute the Z transform of x of t plus n capital T. So in this proof, I'm using the continuous. I start from the continuous time. Okay. So with some abuse of notation, I want to compute the Z transform of this signal, and this means that I want to compute the Z transform of x of k capital T plus n capital T. Okay. So just to make you also understand, so use a bit of different notation and make you understand that when we are shifting of sampling times. So if we consider here k times capital T instead of just k, then we are shifting not just of n, but of n capital T. Okay? So this, by definition, is equal to the sum with k that goes from 0 to infinity of x of k capital T plus n capital T power times z power minus k. Okay? So this is the definition of Z transform applied to that particular signal. Okay? So like in the previous case, the first thing that we do is multiply and divide by z power n. Okay? So we add this bit here. Obviously, it doesn't change anything because we are just multiplying and dividing for the same term. So we are multiplying for 1. So we multiply and divide for that. And now we write this expression as z power n. So as in the previous case, we bring outside z power n because z power n does not depend on k, and we can do it. So we have the sum now of k that goes from 0 to infinity of x of k capital T plus n capital T. And then here we put together this z power minus n with z power minus k. So we have z power minus k plus n. Okay? Okay, let's recover a bit of space. And from that point, we rewrite it again. So we have z power n that multiplies the same guy. So I just write exactly the same thing here. Okay. And now I'm going to add and subtract the same quantity. Okay? I add and subtract the same quantity, so nothing will change. Okay? So now I will add the quantity k from 0 to n minus 1 x of k capital T z power minus k. So I added this quantity and I remove this quantity. So nothing changed, okay? But what is now that actually we can notice? Well, we can actually put these together. And the reason is the following. Let's look at this sequence, okay? This sequence is a sequence that goes from x of 0 capital T, z power 0, okay? So the first term, so let's now look just at this. And we have that the first term there is x of 0, z power 0. And then we have that the second term is x of capital T, z power minus 1, plus a lot of other terms. What is the last term here? The last term here is x of n minus 1 capital T, z power minus n minus 1. Okay? Now we look at this other term, and we see what is the first term here. So when we replace 0 inside here, we get x of n t multiplies z power minus n. And then the second term, when k is equal to 1, is x of n t plus capital T, z power minus n plus 1, plus a lot of other terms, okay, up to infinity, okay? So plus a lot of, I can put it here, a lot of other terms. So if we look at this now, we can see that we can put all together, because from here, the next step in this sequence is actually this. So all these terms can be put together. And so here we have z power n that multiplies the sum of k that goes from 0 to infinity of x of k capital T, z power minus k. And so this is actually, this is actually this term, okay? And then what remains is that term over there. Over there, okay? And this is actually what we have on the slide, because this term is the z transform of x. And we have proved the formula that is on the slide. I want to point out now that what we have here is similar to the shifting theorem, you know, on the right-hand side. In fact, on the right-hand side, we take the z transform and we multiply for z power minus 2, minus n. In the shifting theorem, when we move towards the left, we do the same. We take the z transform and we multiply for z power n. In addition, though, we have this other term. What is this other term? This other term is removing, so you see actually the sign minus, is removing the additional term that we have on the left-hand side of the 0, as I shown before in the graph. Okay? So this term is actually fixing the issue that we have to remove the values that are on the negative side of the time axis. This property of the shifting theorem is quite important because it's at the base then of the solution of difference equations, as I already said. In particular, let's look at the backward difference and the forward difference. Okay? So in the backward difference, we have the difference between the value of the sequence at the time k and the value of the sequence at the previous instant of time, so k minus 1. To compute the z transform, so we use linearity. So the z transform of everything is the difference of the two z transforms. The z transform of x of k is just capital X of z. And then we have to compute the z transform of x k minus 1. Using the shifting theorem, the first version, then we have z power minus 1 capital X of z. And so the z transform of this difference is actually this term here. 1 minus z power minus 1, all multiplied by capital X times z of z. The forward difference is a bit more complicated, obviously. In this case, we are computing the difference between the value of x at this instant of time and the value of x at the actual instant of time. We use again linearity, and we have to compute the z transform of x of k plus 1 minus the z transform of x of k. So the z transform of x of k plus 1, we can use this shifting theorem formula, is equal to z times x, capital X of z, so this is a z transform, minus, you see, we have to remove the values of the sequence that are on the left-hand side of the new time axis. So in this case, we have minus z little x of 0. So we are removing one value, and the reason is that we are shifting only of one value. Then here is the z transform of x of k, and then we can put all together, and we get this expression. Okay? So now I want to point out one thing on the board. If we look at the solution of a difference equation, so we actually have x of k plus 1 equal to x of k plus b u of k. Okay? So now we can compute the z transform of this equation. Okay? If we compute the z transform, we compute the z transform of x of k plus 1. And the z transform of x of k plus 1 is z capital X of z minus z x of 0. And this is equal to a x of z plus capital X plus b capital U of z, where U of z is the z transform of U. Okay? So now we can actually shift some terms in this equation, and we have zi minus a that multiplies capital Z, and the other side we have b u of z plus z x of 0. If this is invertible, we compute the inverse, and we find that x of z is equal to zi minus a power minus 1 b u of z plus zi minus a power 1 times z x of 0. So this is the transfer function. Sorry, this is not the transfer function. This is the transfer function. This is the transfer function between input and state. This is the transfer function between initial condition and state. Okay? Again, what transfer function means and the meaning of this expression, we will study it better later on in the course. But I want to show you already that using this theorem, we can write the z transform of this difference equation. I want to point out also that this shifting theorem, so the version with the plus 1, is actually the correct way to characterize this transform. And the reason is the following. So let's get some space here. So I remove the computation. If here we have the continuous time, and we compute the Laplace transform, so the Laplace transform of the derivative of x is capital S, sorry, is S capital X of S minus minus x of 0. On the other side, we have a x of s plus b u of s, where u of s is the Laplace transform of u. And here then we have that x of s is equal to si minus a power minus 1 b u of s plus si minus a power minus 1 x of 0. So we see that also in continuous time we have a very similar expression. Here we have the transfer function between input and state, and here we have the transfer function between initial state and state. Okay? Often in the course of control systems, if it was a short course, you didn't see this piece. Okay? They just, you just may remember that the Laplace transform of this is this without this x0. Okay? So you don't have this piece. Okay? That's incorrect, because the Laplace transform of this is this equation here. And only if the initial condition is 0, then you have only this term. But if the initial condition is not 0, you have this additional term. This is the same in discrete time. You have the transfer function between input and state plus the transfer function between initial state and state. Okay? This would not be the case if instead of using the xk plus 1, we have the xk minus 1. Okay? The next property that we see is the complex translation theorem. So the complex translation theorem said that the z transform of e power minus alpha k sk is equal to the z transform computed at z times e power alpha. So this is actually a theorem that in part we already saw. We saw another version of this a few slides before. So if we go a bit before, we see actually here that the multiplication by a power k can be actually interpreted and used to prove the complex translation theorem. In fact, we can consider that a, in this case, okay, is equal to e power minus alpha. If you replace it in here, you get exactly this expression. So the proof, you can use this argument to prove it, or otherwise you can do the proof in this way. So you write the definition of z transform for this function, and then you see that you can include e power minus alpha and z together as power of power minus k, and you can redefine z times e power alpha as a new variable, and then write the z transform with respect to that variable, replace it back, and then you get this result. So again, this is something that we already saw. The name complex translation theorem is justified by the fact that when you do this operation, you see that the z transform, the argument of the z transform, is multiplied by e power alpha, where alpha is a complex number, can be a complex number. So what happened to your graph of the function is that the point will actually be translated in the plane, the complex plane, by this number. The next property is the initial value theorem. So the initial value theorem is a useful property, and if we go and read it, we see that the question is, what is the limit with z goes to infinity of f of z? And we see that the answer is actually equal to the first value of the sequence. So at first, this seems a quite surprising theorem. Why it's called initial value theorem? It's called initial value theorem because you see that the initial value of the sequence is actually equal to this limit. However, this theorem is actually quite straightforward. In fact, if we look at the proof consists just in taking the z transform, looking at the definition of the z transform for the sequence x of k, and writing down this sum in an explicit way. And then you see that if z goes to infinity, then all the terms that have z at the denominator will go to 0. So all these terms will tend to 0, and the only term that will stay is actually x of 0. So this theorem is actually quite obvious. A bit more convoluted is the final value theorem. So in the final value theorem is basically complementary to the initial value theorem. In the initial value theorem, we make a relation between the first value of the sequence and the Z domain. In this case, we make a relation between the last value of the sequence, so the value of the sequence for k that goes to infinity, and the Z domain. Okay, so this final value theorem it's true if some assumptions are satisfied. So we suppose that all the poles of the Z transform of X are in D minus, where D minus is the interior of the unit circle. So we are basically inside the unit circle. So if it's true, this property, with the exception of just one single pole, then this limit holds true. So let's prove the final value theorem. So to do so, what we want to write is this term and see a bit how this behaves. Okay, so to do so, let's first write x of z, and this by definition is given by the sum x of k, z power minus k. And now we also write z power minus 1 x of z. Now we can use the shifting theorem to compute this. We know that this is actually equal to the z transform of x of k minus 1. So it's the sum with k that goes from 0 to infinity of x of k minus 1 z power minus k. Okay? Now we put these two terms together, so we write it here. Okay, and we know that this is basically the difference between these two. So we have the difference between sum k goes from 0 to infinity of x of k minus x of k minus 1 times z power minus k. Okay. Now, actually, what we want to compute is the limit of this guy with z that goes to 1. Okay? So what happens when, in this case, okay, z goes to 1? So if we replace it, then we have that the limit with z that goes to 1 of 1 minus z power minus 1 x of z is actually equal to, and now I write all the terms. So the first term is x of 0 minus x of minus 1. This multiplies z power 0, but okay, z is actually 1 for all values of k in this case, because it is the limit with z that goes to 1. So it's just this term, and then plus, so the second term with when k is equal to 1 is x of 1 minus x of 0, and then x of 2 minus x of 1, and so on. Okay? Now, what we have to notice is the following. Let's cut our sum. This is an infinite sum. Let's approximate this with just the first term. So if we approximate this with just the first term, first of all, we know that this is equal to 0. But we see that when we approximate the sequence with k that goes from 0 to 0, okay, we just have x of 0. When k goes up to 1, then we have these two terms. And we see that actually this term cancels out with this term over here. And what is left is just x of 1. So when we cut this sequence to k equal to 1, we remain with just this guy. Now let's continue this sum up to 2. So k goes from 0 to 2. And we see that we add also this guy, and this will cancel with this, and we are left with x of 2. So we see that if we continue this up to k equal to infinity, we are left only with the last value, and the last value of this sequence, so this is equal to x of infinity. X of infinity is actually equal, by definition, as limit with k that goes to infinity of x of k. Okay? And in this way, we have proved the final value theorem. So the final value of the sequence can be computed in this way. We go now to talk about the next property, and the next property is the complex differentiation. So the complex differentiation tells you what happens when you take your function x of k and you multiply x of k by k. And we see that the result is that you can compute the z transform of this function as the z transform of the original function x of k. Then you have to take the derivative and multiply for minus z. Okay, so let's look at the proof. The proof is quite simple. Okay, to do it, we start by computing the derivative of x of z. So the derivative of x z is actually equal to this. This is quite straightforward because we have that the derivative of this guy with respect to z, x of k is constant, so it doesn't change. The only thing that changes is this function here. When we take the derivative, we get minus k, so the power, the argument of the power of z, and then the power will decrease by 1. So this is standard derivative that you know before coming to university. So we end up with this expression, then we just multiply we change the sign, so we want to get rid of this minus, so we change the sign, and then we multiply by z. So on the left we have this term, and on the right the multiplication by z will eliminate this minus 1 at the power, and we end up with this expression, and we see that this is by definition the z transform of k times x of k. This property, the complex differentiation, is quite useful because as long as you remember the z transform of the constant function, then you can compute the z transform of the ramp using this formula, and the z transform of the parabola using this formula. So you don't have to remember also these other formulas because of this theorem. Okay. So the last property that we see is the opposite of the complex differentiation, and is the complex integration. Now the proof of the complex integration is quite more involved with respect to the proof of the complex differentiation. So first of all, the complex integration can be applied if the limit with k that goes to 0 of x of k divided by k is finite, is a finite number, is not infinite. Okay? So if this is true, so if the limit with k goes to 0 of x of k divided by k is finite, then this is the formula to compute the z transform of x of k divided by k. So here in this slide we have g of k that is actually equal to x of k divided by k. Okay? So let's do the proof also of this result, and we start computing the z transform of x of k divided by k. Obviously, this is the opposite theorem of the complex, the opposite property of the complex differentiation, because when you apply the complex differentiation, you are computing the z transform of k times x of k. In this case, we are computing the z transform of x of k divided k, and in one case you get a derivative in the z domain. In this case, we will get an integral. So this will be the capital G of z, because we defined g of k as x of k divided k. And this, by definition, is the sum with k that goes from 0 to infinity of x of k divided by k, z power minus k. At the same time, we compute also the derivative with respect to z of g of z. Okay, so it's the derivative of that term over there. Okay, so this is equal to the sum with k goes from 0 to infinity of x of k divided by k. This is obviously constant with respect to z, and then what is not constant with respect to z is z power minus k. So the derivative of that is minus k times z power minus k minus 1. Okay, and this k will simplify, and then what we obtain, we can So this k and this k simplify, and we can bring the z power minus 1 outside. So the minus outside, z power minus 1 outside, and then what is left inside is just the z transform of x of k. Okay, now what we do is just compute the integral of this term. So it's the integral that goes from 0 to infinity of the g of c divided the c in the c. I changed the variable from z to c because I'm computing the integral from z to infinity, so you have to use a different notation. And this, you see that actually this by definition is equal to the limit with z, in this case, with the c that goes to infinity of g of c minus g of z. Okay? Why this integral is equal to this? This is extremely simple. It's much simpler than what it looks like, because this guy and this guy can be simplified. Okay? So let's eliminate these two guys. And then you get the integral of dg. Okay? So this is basically just, if you think in your previous courses, it's just the integral of the x that is equal to x. So the integral of the g is just g computed at the two values. So g computed at infinity, so it's the limit with c goes to infinity of g of c, minus the g computed at the beginning of the interval. And so we get this expression over here. And if we're computing the integral of this part, this is obviously equal to the integral of this other part. So the integral with z, with the variable that goes from z to infinity, like here, of this function here, that is minus x of c divided c in the xc. Okay? Now, what we do is that we can reorganize these terms. And so we can write that, what is the formula we have to prove? The z transform, so this guy here. So g of z is equal to the integral that goes from z to infinity of x of c divided c in the xc plus the limit with c that goes to infinity of g of c. Okay? So we are almost proved the result. The only thing that we have to compute is the value of this limit, but we can use the initial value theorem. We know that the value of the sequence at the beginning, so the first value of the sequence, is equal to the limit of the z transform with the variable that goes to infinity. So this term over here, okay, is actually equal to g of 0, okay, where g of 0 is this guy over here. Obviously, we cannot replace here 0 because we have a division by 0. So this term is actually has to be interpreted as a limit. So this is actually equal to the limit with k goes to 0 of x of k divided by k. And this concludes the proof. Okay? Okay, the last property that we look at is the real convolution theorem. So the real convolution theorem is a very useful property because it's as useful as the convolution theorem in the Laplace domain. So if you remember again the response, the solution of a linear system in continuous time is made of two terms, an exponential that depends on the initial condition, and then an integral of the exponential that multiplies the input u, the input function u. That integral is a convolution integral and is a quite difficult integral to compute. However, when you compute the Laplace transform of that convolution integral, that becomes just the multiplication of x, the multiplication of the transform, Laplace transform of the exponential times the Laplace transform of the input. Here we have a very similar property. When we have the sum, the convolution sum, so this expression like this, then the transform, the z transform of the convolution sum is actually equal to the product of the two single z transforms. Okay? Again, you already saw this property years ago. You maybe don't recognize it, but you saw it, and you use it in basically all courses of systems and signals. Okay? So let's look at this case in particular, so the real convolution theorem, and let's prove it. So first of all, you have to notice that the z transform of the convolution made in this sense or in this other sense is actually the same. Okay, so the two convolutions are the same. And so let's prove this formula over here. So we want to compute the z transform of the convolution sum, so with h that goes from 0 to k, of x1 of h capital T, h2 of kt minus h capital T. Okay? So, by definition, this is equal to the sum with k that goes from 0 to infinity of all these expressions, so the sum with h that goes from 0 to k of x1 ht, x2 kt minus ht. So now what we do, the first step, is actually, obviously, times z power minus k. So this is just the definition of the z transform. So the first step is to extend this sum. So I claim that this is actually equal to the sum with k that goes from 0 to infinity of the sum with h that goes from 0 to infinity of x1 ht h2 kt minus ht. Okay? So why this is true? So this is true because if h is greater than k, okay, so you see that this difference will be negative. And obviously, being the argument negative, then this value will be 0. So it doesn't matter actually this value what it will be, because you will multiply it 0. So it doesn't matter if this k is extended to infinity. So we go, so this h is extended from k to infinity. So we go up to infinity. Now the next step, so the reason why this is true is that x2 of kt minus ht is equal to 0 for all h greater than k. Okay? Now the next step that we do is to do a change of variable. So we set m equal to k minus h. So I change the chalk because it's very bad. So we get this expression. We set the variable m. We define the variable m in this way. And now we replace the terms inside that sum. So this is equal to, so we don't touch this sum. So we have h goes from 0 to infinity. And we leave x1 h of t. Okay. Oh, here I forgot z power minus k. I apologize about that. Okay. Okay. And then the other term, what it remains is also the sum. Now we replace k. So when k is equal to 0, we see that m is equal to minus h. So we have m equal to minus h. And when k is infinity, we see that actually m is infinity, because infinity minus a number is still infinity. Okay? Then we replace m over there, and we have h2 mt. And then we replace also the k in there, and so we have z power minus m minus h, okay? Replacing minus k using this relation. Now we see that this can be written as the sum with h goes from 0 to infinity of x1 of ht, okay? One thing that I want to point out is that I was able to write this term before this sum, so to swap this term and the sum with respect to this expression, is because this term does not depend on m, okay? If this term depends on m, you cannot just swap the sums like this, okay? But this is constant with respect to m, so I can bring it outside this sum. So I have this expression, and then to this expression, I attach z power minus h from here. Again, z power minus h does not depend on m, so I can bring it outside the sum. And then the sum with m goes from minus h to infinity of x2 of mt z power minus m, okay? Now again, we recognize that for all negative values of m, this sum is 0, so we can actually replace the minus h with 0. So m actually goes from 0 to infinity. At this point, we recognize that this is actually the z transform of x1, and this the z transform of x2, and this prove the result.